Okay, in this video, I'm going to be going through question number 18 from the practice exam. This is the hypothesis testing question. So it says only 34% of U.S. workers have a female boss. However, out of a sample of 142 government employees, 61 said they had a female boss. Do these data provide sufficient evidence at the 5% or 0.05 level of significance to conclude that government employees are more likely to have a female boss in the U.S. than workers in general? So in the hypothesis testing process, our first step is always to write our two hypotheses. So part A is asking us for our null hypothesis, H sub O. And part B is asking us for our alternative hypothesis, H sub A. And in this module, we are just focused on proportions. So each hypothesis is going to start with a P for population proportion. And the null hypothesis is always going to be equal to, no matter what. So in all hypothesis testing, we are assuming the null hypothesis is true. We're assuming there's no change, there's no difference, no effect. There's no change from our population parameter. So we want to look back at the problem and determine what is our population proportion. And they tell us that in the first sentence, they say only 34% of U.S. workers have a female boss. So that's just sort of a blanket statement. They're not saying we took a sample to get this 30% value. They're just stating that as the fact or the status quo. So the population proportion of U.S. workers having a female boss is 34% or 0.34. So that is what we are assuming is the truth. So next, for the alternative hypothesis, we're still starting with a P, and we're still going to be using the same value for the population proportion. The only thing that's different is the sign we're using. So our alternative hypothesis is what we're trying to prove. So we're going to be trying to prove that the population proportion is not really 34%. We're going to be trying to prove it's either less than, greater than, or just different from that amount. And so to make that determination, you want to pay attention to the wording in the question. So it was saying, did these data provide sufficient evidence to conclude that government employees are more likely to have a female boss? So that's sort of the position they're taking. We think that government workers are more likely to have a female boss than workers in general. So we think that the population proportion is actually greater than 34%. Part C, it says what type of tail is it? So this has to do with the distribution. If you're picturing that distribution in your head, are we interested in the proportion that is shaded to the left of our test statistic? Are we looking for the proportion or percentage that is to the right of our test statistic? Or it could be a split case. We're looking at both tails or two tails. And we make that decision based on the sign in our alternative hypothesis. So if the sign in our alternative hypothesis is it's just not equal to, that would be a case where it's a two-tail. If in our alternative hypothesis we're saying that the population proportion is greater than a value, then we're going to be interested in the area greater than the value or shaded to the right. If our alternative hypothesis used a less than sign, that would mean we were interested in the values less than or shaded to the left of our test statistic. So in this case, we have a greater than sign. So this is sort of how our distribution would look. And the type of tail that is, since we have the right side shaded, or that's the side of the distribution we're interested in, it would be a right-tailed test. Okay. Part D asks us what the sample proportion is. So we know our population proportion is 0.34. However, researchers have collected some sample data they're hoping to use to prove that the population proportion is really not 0.34. So our sample proportion, p hat, we're looking for the number of successes over the total sample size. So if we go back to the question, it says out of a sample of 142. So that is our sample size. That's the total number of people in the sample, 142. 61 said they had a female boss. So 61 would be the number of successes. Now I just need to type that into my calculator and round to 3 decimal places. And after doing that, I get the number 0.430. So that's what our sample proportion is. So our population proportion is saying 34% of U.S. workers have a female boss. But when we collected sample data from government employees, in that case it turned out 43% had a female boss. So you want to make sure you're keeping those separate in your mind, what the population proportion was and what your sample proportion was. Part E, it says find the mean of the sampling distribution and the sample error. So you want to remember that the mean of a sampling distribution of sample proportions is always going to be equal to the population proportion. And that's something we've already determined. We've already determined the population proportion is 0.34. So that would be the mean of our sampling distribution of sample proportions. Next thing they're asking us to determine is what the standard error of the sampling distribution is. And so we're going to go ahead and need to use our formula for standard error, which is the square root of p times 1 minus p divided by n. And one word of caution here, when we go to substitute in our values, we want to make sure we're substituting in the value for p, not p hat. In other words, I want to make sure I'm putting in 0.34 for p, not 0.43. So I'll go ahead and substitute in those values. So I'm going to have 0.34 times 1 minus 0.34 divided by the sample size, which was 142. And I'm going to go ahead and type that into my calculator and round to 3 decimal places. And that's going to give me 0.040. So the standard error for our sampling distribution of sample proportions is equal to 0.040. Okay. So it was important to find these two values, the mean and the standard error, because we're going to need both of those values as well as the sample proportion to compute our test statistic, which is the next step here, F. So in parentheses behind test statistic, it says z-score. So that's what we're going to be calculating. However, there are different types of test statistics. There's what's called a t-score, which we're going to be looking at in a couple weeks. But for the proportions here, we're just worried about calculating the z-score. So our test statistic is a z-score. And in this case, we determine the z-score by finding the difference between the sample proportion and the population proportion, and then dividing that by the standard error. So first, our sample proportion was 0.430. And from that, we'll subtract the population proportion, which was 0.34. And then we need to divide by our standard error, 0.040. And one thing you'll notice when you're doing these problems, if the sample proportion is greater than the population proportion, you're going to end up with a positive z-score, which just means it's how many standard deviations above the mean. But if you have a sample proportion that's less than the population proportion, you're going to end up with a negative z-score, which is just telling you that it's going to be that many standard deviations below the mean. So I'm going to type that into my calculator. And because we're finding a z-score, this is the one incident where we want to actually round to just 2 decimal places instead of 3. Everything else we can round to 3 decimal places. Z-scores, we just round to 2 decimal places. So after typing that into the calculator, I get a z-score of 2.25. So that's telling us the z-score of our sample proportion. So this is telling us it's about 2.25 standard errors above the mean. And notice it's more than 2 standard deviations from the mean, which is sort of our general cutoff for deciding if something is unusual, whether or not it's more than 2 standard deviations from the mean. And here we have ended up with that case. Our data has given us something more than 2 standard deviations from the mean, so we consider the data we just got to be unusual, which leans us to support the fact that our alternative hypothesis has more weight than our null hypothesis, but we can't make that decision by just the z-score alone. To make that determination, to see if it's unusual enough, the sample data, we have to actually calculate what's called the p-value. The p-value measures the strength of our evidence. And again, the p-value is the probability of observing a statistic or sample data that is at least as extreme as the one we just got from our sample, given that the null hypothesis is true. So it's helping us determine how unusual is our data. Is it unusual enough for us to reject the null hypothesis and say that the true population proportion is not 34%? Or is our sample data really not that unusual, in which case we would fail to reject the null hypothesis and continue with the assumption the true population proportion is 0.34. The smaller the p-value is, the stronger the evidence is against the null hypothesis. So that's what's next, part G. What is our p-value? So our p-value is what is the probability of us ending up with a z-score greater than or equal to 2.25. given that the null hypothesis is true. So this is where we're going to need to use our graphing calculators, and we're going to use our normal CDF function. So remember, the first two values we enter in are our bounds, our upper bound and our lower bound. And if you remember, we had said earlier that this is a right tail test. So we're interested in the right tail of the distribution. So in this case, our low bound is whatever our test statistic was, which was the 2.25. And the shaded area continues on to the right forever and ever indefinitely, which means our upper bound would be positive infinity. So our low bound, or the smallest value we're interested in, is 2.25. Our upper bound, or the largest value we're interested in, is positive infinity, 1e99. And then the last two values are the mean and standard deviation. And that's going to be easy for us because we're working with a z-score. So remember, anytime we're working with z-scores, we'll always have a mean of 0 and a standard deviation of 1. So I'm going to grab my calculator and I'm going to hit second vars. And that gives me the list of distributions. I'm going to go down to the second one, normal CDF. I'll hit enter. First thing I'm going to put in the lower bound, which was 2.25. Next, our upper bound, which was positive infinity. So I'm going to type in the number 1, and then I'm trying to use this EE right here, so I'm going to hit second comma 99, and I already have in our mean of 0, standard deviation of 1. I'll hit paste. If you have a different version of the calculator, this might be all you see. You might not have had that screen I just had previously. It might just have you enter those 4 numbers horizontally like this. And I'll hit enter. And I'm going to go ahead and round to 3 decimal places. So I have a p-value of 0.012. So remember, our p-value is measuring the strength of the evidence we gathered. How unusual is it that we, from our sample data, got a proportion of 43% when the actual population proportion is 34%? Remember that the smaller the p-value is, the stronger the evidence against the null hypothesis and for the alternative hypothesis. So when we're having to make the determination of whether our sample is significantly different from the parameter, and what conclusions we should draw about the null hypothesis. To make that decision, we're always comparing our p-value to the level of significance. Right, so I'm looking to decide, is our p-value less than or equal to the level of significance? If that's the case, we would say, yeah, it is statistically significant, and we're going to reject the null hypothesis. Our evidence is strong enough to support the alternative hypothesis. If, on the other hand, p is greater than the level of significance, we would fail to reject the null hypothesis. So that means the sample data we gathered isn't strong enough to support the alternative hypothesis. It's not strong enough to show that reality is different than what had been previously assumed. So, in this case, our p-value is 0.012. So, I'm trying to decide, is 0.012 less than our level of significance? And that we get from our problem. So if we go back to the beginning, they'll tell us what the level of significance is. And that's sort of determining how strict you are about your data. This has to be determined before you've collected any data. You can't wait till you've gotten your p-value and then decide what level of significance might be most convenient. That would be very unethical. So here our level of significance was 5% or 0.05. So this is what I'm looking at right now to make my decision. Is our p-value 0.012 less than the level of significance 0.05? And it is. And so that helps us answer this question about whether our sample is significantly different from the parameter. So remember that statistics go with samples and parameters go with populations. So don't let that word throw you off from the parameter. They're just referring to the population proportion. So because our p-value was less than the level of significance, that means yes, it is statistically significant. So to answer this question, is your sample significantly different from the parameter? Why or why not? So we already said we can go ahead and say yes. The sample is significantly different from the parameter. Because, and the because always has to do with our comparison between the p-value and the level of significance. So yes, the sample is significantly different from the parameter because our p-value is less than the level of significance. Okay. So what is your conclusion about the null hypothesis? So because we determined our sample was statistically significant and our p-value was smaller than the level of significance, that tells us we want to reject the null hypothesis and support the alternative hypothesis. So I can say we should reject the null hypothesis and support the alternative hypothesis. And so keep in mind, for a question like this, what is your conclusion about the null hypothesis? You really just have two choices. You're either going to reject the null hypothesis or fail to reject the null hypothesis. So last, interpret your conclusions in the context of the problem. So we want to go back to what this problem was actually talking about and make sure we're addressing the question, addressing what our results mean in this specific situation. And you always want to include in your answer what the level of significance used was. That's sort of establishing how strict your criteria was in making this decision. So our level of significance was 0.05 or 5%. So I'm going to begin my answer by saying at the 5% level of significance. The data, and now we want to think what the data supported. Did it support the null hypothesis or the alternative hypothesis? And what were those hypotheses? What did they mean in this case? So we had decided that we were rejecting the null hypothesis and supporting the alternative hypothesis. And here I'm sort of trying to explain our solution in everyday language. So I don't want to just say the data support the alternative hypothesis. I don't want to use that phrase necessarily, alternative hypothesis, but I want to explain what the alternative hypothesis was. So I'm going to say the data support the claim that, and remember what we were comparing was the proportion of female bosses in general to the proportion of female bosses in the U.S. government. The alternative hypothesis was that the proportion of female bosses in the U.S. government was greater than the proportion of female bosses in the U.S. in general. So the data support the claim that in the U.S. government, employees are more likely to have a female boss. And I don't want to just stop there. I want to make sure, so I'm saying the U.S. government employees are more likely to have a female boss compared to what, right? I don't want to just stop there. More likely to have a female boss than workers in general. And I want to check back with the problem. So not just workers in general, but U.S. workers in general. So at the 5% level of significance, the data support the claim that in the U.S. government, employees are more likely to have a female boss than U.S. workers in general.